Hey everyone, in this video we're going to take a look at how OSPF does its type 7 recursion, and we call type 7 is the external routes from an NSSA. So before we get into it, I'll just do a quick overview of the topology because it's changed a little bit. If you've been watching some of my last videos, the physical topology is the same, but basically what we have now is these links over here are going to be in area 456, which is an NSSA. We have one external route, which is the loopback of 6, which is being redistributed into OSPF. Basically, here is going to be 0, and for the purposes of this video, this is really all we're going to need to take a look at. So what we're going to do is take a look from R3's perspective, because R3 is a completely is in area 0, all of its links, and see how it recurses to get to the loopback of 6. So let's head over to 3 and let's do a show IP OSPF database and see what we have. So right off the bat, you could see that we don't actually have a type 7 LSA on R3. And this kind of brings us to the first thing we need to learn about type 7 LSAs is we have a type 7 to type 5 a type 7 to type 5 translation that occurs on the ABRs. So let's take a look at show IP OSPF border routers. And we can ignore router 2 for now. I mean, router 2 is a border router to go to this area. That's fine. But let's take a look at 5 and 4. So 5 and 4 are both seen in the topology as an ABR/ASBR, and they're in area 0. Now, specifically, the reasoning here is that type, even though R4 itself is not doing any redistribution, it's taking, and let me just change color so we can have a clearer picture. It's taking the type 7 LSA from here, and it's translating it into a type 5. So because it's creating the type 5, it becomes known as an ASBR. And it's the same with 5. 5 is learning a 7. It's translating it into a 5. And because it's creating a type 5, OSPF sees it as an ASBR. Even though from our point of view, if we were to just take a look at maybe do a show run, and we would see that 4 and 5 aren't doing any redistribution, we would think that it's just an ABR. So just something to take a look at when you're viewing this show command. So how is this all working? Let's go ahead and take a look at one of our LSAs. Or actually, before I do that, let's take a look at the type 5 LSA that we're learning. So show IP OSPF database for external. And let's take a look at what's going on in the type 5 LSA. So we can see the external network number is 6.6.6.6, which makes sense. So let's go here. We have an external network with 6. The advertising router is all 5s. The forwarding address is 10.0.46.6. So if we remember in our last couple videos, the forwarding address had pretty much exclusively been all 0s. And in that case, if it was all 0s, all we did was take a look at who our advertising router was and do the recursion that way. In this case, the forwarding address doesn't actually match up with the advertising router. So what we have to do is now, instead of recursing there, we have to do recursion here to figure out how to get to this forwarding address. So let's erase this. We know it's 10.0.46.6 is the forwarding address. So let's just try to make diagram 10.0.46.6. Excusing my awful penmanship. This is the address. Let me clear that up because that's just horrifically bad and illegible. I'll just say 46.6.6. How about that? This is the forwarding address to get to 6, which, by the way, it's a type 2 with a metric of 20, so we know metric is 20. Okay. So now how do we do recursion to get there? Well, obviously we could just do a show IP route, but that's not the way we're doing things. Let's take a look at the OSPF database. Okay, 10.0.46.0. We have a summary netlink state for that route. So is that the way we want to do it? Let's take a look at some of our other ones. We don't have that anywhere in our routers, and we don't have a netlink state for that either. So yes, summary netlink states, the type 3 LSA, we have one, and we actually have it from 2 locations. We have it from router 4 and from router 5. So let's go ahead and show IP OSPF database. And we're going to do a summary. 10.0.46.0. So we can see we have 2 of them. And I'm going to go ahead and make this a little bit larger so we can see. And we could see a couple things here. One of them is being advertised by 4.4.4.4. Okay. And the other one is being advertised by 5.5.5.5. But if we look, we could see the one from 4.4.4.4 has a metric of 1, where the one from 5.5.5.5 has a metric of 2. So here we go. We have 2 choices. We have 5, the metric of 2, and we have 4 with a metric of 1. Okay, and now we could do our recursion to both of these type 1 LSAs. So let's first take a look at, from our perspective, or actually let's take a look at how to get to the type 1 for 4. And just to make sure we're keeping track, so far what we've done is, from R3's perspective, is we've gone from 5 to a type 3, and now we're looking at the type 1s. All right. You'll notice that there's no type 4 LSAs. And again, that's because the ABRs are creating the type 5s. So if you remember back in the videos, or if you just remember how this works, when the ASBR is internal to the area, there is no type 4 LSA. The type 4 LSAs are only created if it's an inter-area ASBR. So now that we're looking at the type 1 for 4.4.4.4, we can see that we have our stub network, which is the loopback of type 4, and then it's connected to a transit network, which is 10.0.234.4. So 4 is connected to this DR with a metric of 1. And if we dig into that DR, let's do a show IP OSPF database network. That 4, we can see we have routers 4, 2, and 3 are connected. Since we are R3, we know that's going to be us. So we're connected to 4 with a metric of 1. Okay? Now from 5's point of view, how does 5 get there? And actually we could draw 2. We could draw 2. So the metric from here to here is 1 as well. So let's take a look at 5's, because this is our other ABR. And the link to 2 has a metric of 1. So let's say here we have a metric of 1. So the total forwarding from 3 to get to 46.6 is going to be 1, 2, 3, 4. So the metric of this path, and it's actually going to be the forwarding metric, equals 4. On this path, it's 1, 2 equals 2. And remember, the metric is going to be 20 because it's a type 2 route. So if we look in the routing table, show IP route, six. Here's the interesting part. Our forwarding metric is 2, which we see it would be the best path. So just doing, you don't need to do any crazy calculations with OSPF. You can just take a quick look if you draw it out and say, oh yeah, we're going to prefer the route through 4 instead of preferring the route through 5 because the forward metric is 2. Okay, that makes sense but because it's an E2, the actual metric is 20. So again, to reiterate how external type 2 work. Yes, the metric in the table will be 20 on all the routes as opposed to an E1, which will add all these together. So if we did an E1, the metric would be 22 in the routing table, or for this pass, it would be 24. But the metric in the table is 20, but OSPF will still look at the forward metric when it tries to recurse through the graph to get to that destination. And this is a really interesting case because we can see we're learning this from 5.5.5.5, but that's not the path that we're actually taking. So let's take a look at just quickly get rid of this. Let's just take another look at that Type 5 LSA, and we can see show IP OSPF database external. So we can see that here. And it's very interesting because it works differently than if the forwarding address was all zeros. We see the advertising router is 5. We see the forwarding address is here. But we're not recursing to this address. We're recursing to this address. And when we do that recursion in the OSPF database, we're not using 5.5.5.5 in the path at all. We're going to go through 4. So again, when you're looking at a Type 5 LSA, you really have to look at the forward metric in order to see where the data is going to be going through. Because if the forward metric was all zeros, then yeah, sure, we would be going through 5. But that's not the case. So that's how a type 7 LSA is kind of done with recursion outside the area. It's actually just type 5 recursion. So it's really not much different than something you already knew. And as you can see, we went from 5 to 3 to 1. We didn't even involve the type 7 at all. So the last thing I just want to take a look at in this video is we can see that router 5 is the router that's doing the advertising for that. So let me clear the screen. When R6 creates the type 7 LSA, it sends it to both 5 and 4. Why on R3 were we learning it from 5 instead of learning it from 4? Because both of these routers should be doing the type 5 to type 7 translation. Well, here's why. We have something that we call the type 7 to type 5 translator election. And that means that R4 and R5 will hold an election to decide who is going to flood the type 5 route into the area. Basically, this is done because there's no need for there to be multiple copies of the same LSA, especially with the forward address done the way it's done. So it would be different if the forward address was all zeros, because then we would want every ABR to flood that in the area so that we can have R3, for example, choose between R4 and R5, which is the best path to get there. But because the forward address is here and we have to recurse that anyway, there's no need for there to be multiple copies, especially if we had, I mean, even let's say we had 5 routers that were doing the that were ABRs between area 0 and area 456. We don't need 5 copies of the same LSA when just one will do the trick. So how do we choose who does the translation? It's actually pretty simple. It's the it's the ABR with the highest router ID. And we can look at which one has the higher router ID by just going into any of the routers in that area. Show IP OSPF Database. And we can see our link IDs. We have 2, 3, 4, and 5. And we know that between 4 and 5, 5 has the higher router ID. So 5 is the one that does the translation. So let's go ahead and make a change and we'll see what happens. Let's go to R4 and router OSPF1 router ID. Let's make this, instead of 4, let's do 44. Now we have to reboot the router or clear the process in order for it to take effect. So obviously a change we wouldn't want to do in a production environment, but this is a lab, so we're just going to clear the process. Yes, we're going to reset the process. We'll let it converge. We'll go back to R5, take a look at the database, and we can see that we still have this, which is going to age out in a moment. But now we have 44444. So what should happen is, from R3's perspective, if we take a look at the show IP OSPF database, we can see we now have 2 type 5 LSAs. And I don't have any fast convergence optimizations going on in OSPF. But you could just take a look by the age what's going on here. This is the LSA we were looking at before, which is a high age. Eventually, we're going to age it out. Now we have a new one, which is much younger, from 44444. And if I went across all my routers, and let's just go ahead and we'll just speed things along. OSPF process. Cleared OSPF on all the routers. Take a look at the database now. We're going to be converging very slowly. Let's take a look at R5 and just double check the database here. Okay, so from R5's perspective, where am I? Area 0, area 456. We could see that 4.4.4.4 is no longer in there. Okay, so now that we've converged, this is interesting. So we still actually are getting 2 Type 5 LSA external link states, which is not the behavior that we should be seeing. So let's okay. So that might have been just another OSPF converging issue. So now we see correctly. We're just learning the Type 5 LSA from R6. I mean, from R4, which is 44444. So the highest router ID between the ABRs will win the election, and that is the router that will be doing the Type 7 to Type 5 translation. And again, the reason why we only need one to do it is show IP OSPF database external is because of the forwarding address. It's not all zeros. We're not recursing to here. We're just recursing to the forwarding address. So it really doesn't matter which ABR does the origination. We just need to make sure that one of them does it. And now, what happens if R4 goes down? So let's take R4 and we'll go into this link and we'll shut it down. And we'll also go to gig 1. We'll just simulate a total failure. We'll say R4 totally shuts down. Show IP OSPF neighbors. All right, R4 has no more OSPF neighbors. Totally shut down. If we take a look at this external now, again, it hasn't aged out. Let me just quickly pause the video to try to move this along. My lab is a little slow. Okay, so OSPF database will begin with Type 5. So now we could see we're learning it from 5. So 4 was shut down. Even though that was the one doing the Type 7 to Type 5 translation, it doesn't matter because now Type 5 or R5 takes over. And if we show IP OSPF database external, it basically looks the same exact way. The only difference now is that when we recurse to this address, since R4 is down, we would recurse through R5 and our traffic pattern would change. It would just go this way this time. So this is just how Type 5 or Type 7 to Type 5 translations work. This is how recursion works with the Type 7 LSAs, and this is also how the forwarding address works in the OSPF database. And we also learned that with a type 7 LSA, there's no need for a type 4 LSA like there is with a type 5. Because remember, with the type 5, it was being generated outside the area, so the type 4 LSA was needed to tell to tell the routers within the area how to get to the ABR to get to the ASBR. With a type 7, since these ABRs, routers 4 and 5, are creating type 5, the routers in area 0 don't need another type, they don't need a type 4 LSA to tell them how to get there. They're already within the area. So I hope this is clear. Pretty long video, but it covers a lot of topics. So, leave any comments or questions below.